Okay. So yeah, really, basically, I was over the Thanksgiving holidays just doing nothing and then thinking about the stuff on the plane and had a couple of ideas, several things we talked about before, and they're not super new ideas, but I thought it was pretty relevant to what we talked about in the last meetings, kind of talking a bit more about object behaviors. So I just kind of wanted to put it all in one place, and most slides are actually more about kind of framing the problem instead of the concrete solution. And then towards the end, I have a couple of more speculative ideas about how the brain might be implementing this. And we can do more brainstorming or have like a shared whiteboard or something.
Yeah, just to remind you, I think I wrote about this on Thousand Brains. It's like, I've always found that if you completely describe the problem, then the answer is obvious. So to me, describing the problem accurately is the most important thing. So no, don't have to make excuses about that.
Yeah, hopefully these few slides will help with that, kind of spark some interesting discussions and ideas in all of you. So yeah, why talk about object behaviors if the last weeks we talked more about like policies and decomposing policies and goal states and stuff like that. But I think all these policies we talked about, they aim to change an object from one state into another, or aim to change the world from one state into another. And how an object changes from one state into another is modeled as an object behavior. So I think to understand policies, we first need to understand how object behaviors are modeled. Or at least if we understand that, it will be a lot easier to talk concretely about policies and what exactly learning modules might be communicating to achieve goals. So I thought I'll start with just kind of defining what is an object behavior, or how would we represent an object behavior. And this is just my stab at that. So I would describe it as a sequence or space of states that can be navigated through actions or time. So for example, the stapler can be in several different states.
Okay, how did you make that animation?
I downloaded them. Credit
Oh,
download.
I was gonna say, you got too much time in your hand if you made that one. That's pretty cute.
No, I just got them. But yeah, basically it can be open, it can be closed, it can be in several states in between, and we have kind of a model of how it can navigate from between these states. So it can't just randomly jump from open to close. It has to go through several intermediate states. And we also have a model of how actions can move the stapler through that state space. And we have other ones where we're actually not changing the locations of the object, but actually features. So for instance, turning the lamp on or off. Then we have states that have a bit more of a continuous space that you can navigate through, like a joystick, where maybe you even need some path integration properties to kind of model how you can navigate through that state space. And then we have behaviors that aren't necessarily affected by your own actions, or that just kind of change over time. And then we have like very complex behaviors of compositional objects, like a human running around. But I would say all of them can be described as like a set of states and kind of rules of how you can navigate from one state to another state, whether it's just by the passage of time or actions that you exert on that object or actions someone else exerts on that object. And then,
Sorry, I'm just curious, what website did you use to get these? These are really nice. They're even like kind of on brand almost in terms
of. Yeah, I tried to get like consistent colorings, but
right.
It's from FreePic. They have like thousands of these little animated
Okay,
icons.
but so this is through your selection process that they match like their
Yeah.
color schemes so well. Okay. Yeah, they're really nice.
Yeah. I couldn't get it for all of them. Like these two, I didn't find like a bluish version, but yeah, some of them worked out nicely.
The little Newton's Cradle looks like it's almost like the old Memento logo, you know.
Yeah.
Of course, it's not operating properly. The middle two shouldn't. Close enough.
Yeah.
Cute.
So yeah, a couple more requirements. So behaviors should be transferable to objects with similar morphology. So if I learned how one stapler works, how this one works, I should be able to apply that behavior model to other staplers that have slightly different shapes or color, or even a bit of a different concept here. Or even
I would
like
go,
something I've never, yeah.
I'd go even further, say like, these behaviors are transferable to the object it's transferred to may not have similar morphology, or at least much of it may not have similar morphology. Like the hinge on the stapler could be applied to anything with a hinge, which might have very, very different morphology, but it has some attribute of the same. There's some part of the object is similar. And the behavior applies to that part, right?
Yeah, so here's this kind of example of like the behavior of running, and you can apply it to a totally different object, like a banana. I mean, you kind of have to add some X, which is what I mean with a similar morphology, because you have to have these parts that are actually moving that define that behavior. But
yes, almost like a correspondence in morphology. Like as long as there's some subset of the graphs or the morphology that kind of can map onto one another.
Right, like a hinge could be anything could have a hinge, but
there could be multiple hinges, or
or as long as the part that looks hinge-like is there.
Yeah, exactly. So yeah, I didn't mean to say that you can only apply that behavior to other objects of that class of objects like staplers, but you could also apply it to like totally different objects. You could imagine a banana stapler, and you can imagine or recognize totally new combinations. Like you may have never seen a running banana, but now you see it and you could easily identify that it's a running banana. So yeah, that's the one. Behavior should be transferable to objects. And then also one object can have multiple behaviors, like a human or a banana can be dancing and walking and running. And it always stays that object is always a banana, but it has all these different behaviors. So these two requirements kind of lead me to say that behavior models are separate from feature and morphology models, in the sense that similar to how we can have an object with this, like objects with the same morphology but different features on them, like a coffee mug can have tons of different patterns on it, or logos. Similarly, we could have behavior models that can be mixed and matched with different feature and morphology models. And that kind of implies that different morphological models need to be mappable to the same behavior space, or at least a range of them. So for example, if we say an object has a unique location space, or the locations are unique to that object, the behavior model needs to somehow be able to map onto all of these different location spaces of different objects. And this one I'm just kind of throwing out here. This is a bit just something I was thinking. I don't know if you would agree with that, but similar to how we kind of said that morphology is more important than features, and that I would maybe make the claim that behavior is even more important than morphology. Like often we define objects by their behavior, like chairs don't necessarily share a lot of morphology, but the way you interact with them kind of can define that category.
If you use a slightly different language, might be better. The language I would say here is which of these might have precedence in sort of a processing in a learning module, right? So that may be one way to look at it. What's more important? It's hard to say what's more important, but which has, which, if you see something that has, that has a, I'm trying to imagine in my head, but I might agree if I thought about it more, that behaviors, if I recognize there's a potential behavior in an object, that might have precedence over more processing precedence, or attention precedence over something that says, oh, it looks similar to something else.
Yeah,
or the
one
features.
example I was thinking there was like, you can animate a totally usually inanimate object like a lamp in the Pixar logo, and it suddenly becomes something totally different. Like you give it like a personality, and you can kind of predict what it's going to do next and stuff like that. And I mean, a lamp in general is, I feel like, a good example. Lamps can have absolutely different shapes, but what makes all of them lamps is that you can press a button and the light turns on. So yeah, that's why I was kind of throwing this out there. I'm not sure if it makes even a difference, but it's just something I was thinking.
I think it's, I think it's a nice way of framing it, just in terms of like, certainly in terms of what we care about as agents that interact in the world is generally the behavior of things more than the morphology, just because that is what impacts their affordances or how we can interact with them, how we can change the state of the world. So it's like, in the same way that we're not just like a classification system or whatever. So like, that's why morphology doesn't matter as much.
Right. I agree. A few weeks ago, I was talking about these topics, and I made a proposal which is just slightly variation from what you proposed here. I was suggesting that the way to think about this is you have models or location and features, right? And features at locations, in that both, that you could describe all the things we talk about by saying any one of these things can change. The features at a location can change, or the location of a feature can change. And so the entire model can change, but by just mixing those two combinations, right? So a feature could be like a red light turns to a green light, or the stapler is one part of the stapler moves to a new location relative to the stapler. So in a little bit more general, say there's really only two things that you basically have: features and locations, and any combination of that can change suddenly or smoothly, and that describes the entire space of objects, of a particular object. So I guess I'm saying that instead of saying morphology is more, is less important than behavior, I think models can, as long as we agree it's the same model, the same object, that anything can change in that basic simple idea that any of the combinations of the model can change. I can give examples of where features move, where features change, where orientation of features change. And so I can get rid of sort of the morphology idea. It's just like locations and features, and any combination of those can change. And we can describe all the different things we're talking about here that way. It's a little bit, I think it's a little higher level, and it's only really, it's a slightly different way of saying the same thing that you're saying, but it feels a little bit more general purpose.
Yeah, I think that's a good way of putting it. Like, while like if you have one behavior of an object, all of the features and all of the locations could be changing while going through those sequences of states. So,
right. Or maybe it's not even a sequence. Maybe it's just sudden. The object could be, the light could be on or off, so it may not be a sequence in between, or it can suddenly pop into a different shape. Anyway, I think it's just I'm trying to move away from this concept of morphology as a separate thing, and it's really just like you've got locations and features, and any of those things can change in any way, and the features have poses, and features have poses and locations. So it'd be simpler than what you propose here. It'd be a superset of this and stuff.
Yeah, and when I'm talking about morphology, I basically mean just the model of locations and orientations relative to each other.
Right, I know that, but I'm saying you could just replace the word morphology greater than features and just say we have models, and by and I just define what a model is, and then anything which changes that model, any of its attributes could be considered behavior, or it could be states of the object. It's all the same.
Yeah, I would agree with that. Yeah.
I was always bothered by the even though I was using it for quite some time, this idea of a morphology model just didn't seem right to me. So I think we can just generalize it to say, well, morphology is a word we use sometimes, but it's not necessary, actually.
Yeah. Yeah, I'll keep using the word in these slides, but
Yeah, of course.
Yeah. Yeah, definitely understand the point. Yeah. Okay, yeah, last kind of slide to recap the kind of outline and requirements. So key ideas I'm kind of proposing or repeating here. I know we talked about this many times before. So that there are 3 types of models: feature, morphology, and behavior. Feature and morphology can be in different states. So state conditions which features will be observed at what locations. So depending on which state the object is in, like you just said, you might see totally different features, and they might be totally different locations than if the object were in a different state. And then the behavior model represents how to transition between different states of the feature and morphology models. And I just put this here, I'm not sure about it yet, that it would be nice if this behavior model would have path integration properties as well.
Yeah,
but I'm not.
I agree with that. In fact, remember when I was talking about how the behavioral model might be in the upper layers, and I felt the same way, because when you want to generate a behavior, you want to move some object from one state to another. It's just like moving your body from one location to another, right? You want to be able to do that on a path you've never actually traversed before, right? You want to be able to say, oh, how do I get from point A to point B, even if I've never done that before? And I felt that would be a similar property you'd want to have in behaviors.
Yeah.
Where you said, right,
Yeah, I
want
think
to get
the
to
reason.
the behavioral state, you know.
Yeah, the reason I'm saying I'm not sure about this is because I was having a very hard time coming up with an example of like a behavior where you would have never observed a certain transition, because it seems like there's only a limited number of behaviors, and we usually have a lot of exposure to them. Like even the joystick example, you could theoretically, like if we can't find a mechanism that can do this with path integration properties, you could theoretically learn a detailed transition model of every possible transition of the joystick. And then when you see an object that has similar properties, like your arm, limbs are similar to a joystick, you can just apply the same behavior model to it. Like I couldn't think of one example where there's like a totally new behavior that I haven't seen on a different object that I couldn't just apply to.
Yeah. Well, I feel like kind of what I feel with path integration, it's more like, yeah, every edge needs to be observed, but
Yeah, and that's what I mean.
But a particular path does not need to have been observed. So that's the difference between just memorizing a sequence.
Yeah.
So if you've observed every edge, and then you could follow a novel path using those edges. But of course, if you've never observed an edge, then you don't know that it exists, and you don't know you can use it.
So it's interesting. I see your point that I have to spend a little bit of time thinking, see if I can come up with a counterexample, but sitting here right now, I can't. The reason I propose that path integration might work is more of an elegance argument. So that could be wrong. The elegance argument is that, oh, wow, it looks like you've got these motion sensitive cells in the upper layers and your motion sensitive cells in the lower layers. The ones in the upper layers seems to be object movement, and the lower layers seems to be movement through the world, sensors to the world. And so I just said, oh, well, let's on the assumption assume that the same mechanisms are at play. And so if we have grid cell-like mechanisms in the lower layers, we could have grid cell-like mechanisms in the upper layers. And then path integration might come for free. It might be part of what we know that grid cells do that. So that my argument was more of an elegance and a simplicity of design argument, but those are often wrong. So I think your point of that you have trouble coming up with an example is pretty poignant. So maybe I'll try to see if I can come up with some counterexamples, but I'll accept your point for now.
I feel like a general example might just be like if you imagine you have like 2 states, like an intermediary state and a final state. let's say it's, yeah, I don't know, filling coffee in the machine and then like powering it on or something. I don't know. Then you might have learned multiple edges or experienced multiple edges into the first one and then multiple edges between that one and the next one. And so I feel like this is where like that sequence of two edges you may have never traversed, but you'll have experienced every edge, and so you can combine them in novel ways. Like,
Well, maybe.
so the point is like, I guess it's different from just like memorizing the whole sequence, because of course, as the sequence becomes longer, then like there's this huge space you could explore, which if you have to like visit the whole sequence, you'd be more constrained in your behavior. Or like if you have to have experienced the whole sequence.
Yeah, I can think of examples of solving problems where we're doing it in a very novel way, a way I've never done it before. Perhaps, maybe you can argue otherwise. Imagine I just want to pour coffee into a coffee cup, and for whatever reason, there's something at the top of the pot, coffee pot is blocked or something. And then I said, oh, look, there's a little drain hole on the bottom of the pot that I can open up. And so I decided to fill up my coffee cup. I opened a little drain hole and then it come out the bottom of the pot. And sort of, you know, it's like, okay, I've never done a coffee pot like that. I don't know if I've ever filled the coffee cup like that. Of course, I've seen other things with holes in the bottom where water comes out. I'm not sure that's a counterexample or not, but it is. I'm thinking of examples like, well, I'm solving this problem in a very novel way for coffee. But maybe.
Yeah, I think a copy one's, or go ahead, Vivi.
I was just going to say that example sounds a bit like applying a different behavior to a novel object, like applying the drain hole to the coffee pot.
But I had to somehow figure that out, right? It's like, yeah, I'm not sure it's a counterexample. I'm just thinking out loud. Okay.
Yeah, I mean, like one other.
Go ahead.
Just like one other example with the coffee one is like, yeah, let's say for whatever reason, like I need to put the fluid into one vessel before I put it into the second vessel. Like that's something where, okay, maybe the first time I experienced it, or like when I normally do it, I always kind of use like, I don't know, the sink to fill it up or something like that. But then you're in your situation, Jeff, where there's like no water in the house or something. So you have some other source. Like that's where you're kind of like following a different edge. Like you've filled up vessels with other things before other than sinks. So although you've normally not followed the sequence, like normally your sequence of making coffee isn't like, it is to fill up with a sink and then pour it into the pot into the machine. But because you understand this edge of like, oh, I can also fill up the pot first with like some other source of water, then you can like follow a novel path.
Let me.
I guess I just feel like,
let me talk about what we think about path integration in terms of like grid cells in navigating an environment. So the animal is moving around and it needs to get home. And so it says, oh, I need to get home. I'm going to follow go straight there, even though I've never gone from A to B, I'm going to go from A to B straight. And that requires, you know, what we might call properties of path integration to know where you are after you've moved. And in that case, the animal is still executing a behavior it's done before. It's moved in all directions. It's, you know, if you think about compass directions, it's moved in all directions. So it's taking a behavior. You could say very simply, it has a repertoire of moving in different directions. And so it's applying one of those repertoires, one of those behaviors in a new situation. But we still call that path integration. You know, you might say, well, it's traversed all those edges before. It's gone in all different compass directions. Therefore, you know, it's not path integration. But I'm not sure how. But we do call that path integration or related to it. So I'm not sure these other examples where the same behavior has been applied elsewhere. Why would not say, okay, it's not path integration anymore? You know.
Yeah, I mean. Well, when I wrote path integration, I was thinking of the example of where you moved from A to B to C, but now you know how to move from C back to A, even though you never moved from C to A, which is maybe slightly different. But I definitely
think that needs to be learned though, because there is an edge. Like if it's an arbitrary space, you don't actually know if it's bidirectional. Like some systems you can only move in one direction.
Yeah, that's what I would say too, that for an object behavior model, you need to have learned, you need to have observed all of the edges basically. Like it's not a space like like 2D or 3D space where you kind of know how that space works. It's a more abstract state space. So
Yeah,
it
but
seems like you need to have observed those edges.
I'm not giving up yet on this because I think it's still a good idea. To me, what's important is, I mean, sometimes path integration, oh yeah, I go from A to B to C, therefore, I could have gone other ways to C. But I was thinking in terms of the behavior, you're trying to achieve a goal, right? So that's what we're talking about here, ultimately, achieving a goal. And so the animal wants to get home or to a safe place or back to the food. And so it traverses a path through the environment that it's never traversed before. But it can calculate how to get from its current location to desired location. The equivalent in the object state space or the behavioral space is that the object is in some behavior and you want to get it to a different behavioral state. And you've never transitioned from behavioral state A to behavioral state B. Maybe you've gone to behavioral state B from other directions in other ways, but you're now trying to say, oh, I'm in a new location here in behavioral state. Maybe the stapler is completely open, and I've never made a staple when the staple's completely open is a bad example. But, so what do I have to do to get the staple to come out? Or that's not a very good one. But the point I'm trying to say is that you could make the analogy between, like, I'm trying to go from behavioral state A to behavioral state B. I've never made that specific transition before. I don't have to retrace my steps to get there. I should be able to go right from my behavioral state A to behavioral state B. That would be the goal. That's what I'm thinking about when I'm talking here. I'm not talking about the other path integration A to B to C. I'm thinking, like, how can we calculate how to get from one behavioral state to another directly, even if we've never directly gone there before. I'm not saying, I'm just saying, I just want to clarify what I'm talking about, which is a little different what you were talking.
Yeah, that makes sense. I guess what I was saying here, I'm not saying like we don't need path integration. I couldn't come up with a great example of where we need it concretely, and it seems difficult to imagine any kind of path integration in behavioral, like in state space. But maybe it's possible, and maybe we can use the same mechanism we use for the
right. I don't know. I think it deserves a little bit more thinking.
Yeah, I mean, if we agree that path integration is kind of being able to follow, like being able to make links that don't follow a single memorized path, then would you not agree we kind of need that? Like we clearly can't just like learn a single sequence and then always use that sequence.
Yeah, no, I agree with that. We wouldn't want to have to memorize sequences. We would want to be able to move from edge to edge in novel combinations. I just mean, what I meant with path integration is I can't infer an edge that I've never seen before because I don't know how these abstract states relate to each other.
So you're right in the sense that, why did the balloons come up? What happened?
I don't know, it's some kind of gesture recognition.
Oh my gosh. So I mean, it's really good observation. You couldn't think of one. I mean, that's an important observation. But again, if I was thinking like, I was starting with the idea that why would you have, how does the brain process these motions of the object, and which I've been arguing are the motion sensitive cells in the upper layers that have restricted receptive fields. They would clearly sort of represent motions of the object. And so they look very similar, that you have mini columns of these motion sensitive cells that have the same directional. It just looks like the same stuff we see in the lower layers, but with smaller receptive fields. And it's the stuff that we know the grid cells require to build grid cell representations. So I just jumped to the conclusion, like, okay, well, there's probably doing grid cell-like mechanisms up there. And if you have grid cell-like mechanisms up there, then path integration comes for free. But that could be all wrong. Maybe there's no grid cell-like mechanisms up above. But then I'd have to understand, like, well, how does the upper layers process object motion? Which I still don't understand. So I think we can just leave it as an open question that perhaps there is grid cell-like mechanism in the upper layer, in which case path integration would come for free, or maybe there isn't a grid cell-like mechanism in the upper layer, and it just looks like there might be. And so then we need another hypothesis about how those upper layer motion cells are being processed and interpreted somehow.
Yeah.
And I mean, just for what it's worth, I feel like you could argue even with grid cells, like what that's kind of doing is like you've visited all the edges in that you've often navigated over 2D space and realized that like, okay, these basically form edges with their neighbors or whatever. And then when you're in like a novel space, you almost like tiling that space with that behavioral model. But you still at one point had to learn locally that there's this like these edges. And
Yeah,
so like
but
I feel like there's not necessarily any setting where you can kind of path integrate without having like learned the behavior of edges.
Right. And that's true with grid cells. And so I'm saying, grid cells, you must have known you can go in different directions from where your current position is. And so then, but I don't throw away the idea of path integration. Just because I'm doing something I've done many times. It does feel like, it's at a very high level, it feels like I have a problem to solve. I look at my situation and say, well, I know how I want to get this situation resolved. I know what state I want to be in. But maybe I've never started in the current state, and so I have to figure out how to do it. You can even argue this in the table setting thing, right? Maybe the plates and the utensils are in some sort of wonky position you've never seen before, and somehow you're able to, rearrange things to get it right. I'm arguing these points. I'm not 100% believing these points. I'm just arguing for sake of research discussion here.
Yeah, so I guess that would be an interesting one to like talk some more about sometime. Like, how would we use a grid cell mechanism to represent state space, which is a lot more kind of abstract, with more abstract ways to move through that space, or more constrained ways to move through that space. So I mean, I think we talked about it sometime before. How grid cells might be very general and might be able to learn such novel spaces. They're not 2D or 3D. But yeah.
Right. They don't know what they're representing, right? They just say, here's some movement. I'm gonna take the movement, turn into a space. And whatever it means, I have no idea. That's what so it just starts with movement vectors and says, okay, that's my space.
Yeah. I guess that can bring me to the next part of like how this might be implemented in the cortical column, and then we can see about how that matches. So what it was, I took all of these requirements and constraints, and I have this big overview that I kind of work on over the past years, where I just draw all the anatomical connections that have been found. And if you like zoom in, there's like quotes from papers and figures from papers for each of these connections and references. And I just went through it and zoomed through it and figured out which of these could work out for behavior models. And also some of our previous brainstorming notes where we talked about this a bit before, and try to kind of map this. And I'm just going to show a very simplified version, but if we want to brainstorm more, I can also pull up the full view and then show the detailed connections. But yeah, so just to recap, we have the inputs here, the main feature input to layer 4, and then a movement or displacement to layer somewhere between layer 5 and 6, and then an orientation, both of these relative to the object, that the orientation goes like right at the border of layer 3, 4, roughly. And then we have associations that we learn between features and locations down here. And then that can be like after some successive movements, the activations here can be pooled into an object ID, which would then be the main output of the column out of layer 2, 3. And then the second output is the motor output out of layer 5A in primates, at least. And then we have these long-range connections that we talk about as the voting connections. So those are in layer 2, 3, where we usually say that's voting on object ID. And then there are also long-range connections found in layer 5B. And what I'm basically suggesting, or I don't think that's the first time we talked about this, would be that those might be voting on the behavior model, since layer 5 seems to be quite involved with motor and behavior and movement. It's layer 5B, not like layer 5A is the actual motor output to the subcortical regions. Layer 5B has these long-range connections to other models. And I have another slide on another side note on this one, how it might be actually what we refer to as affordances. But then the other two, if we go with this 3 model idea, we talked about this before, that layer 2 is a bit more sparse than layer 3, and how maybe layer 3 is like the general model ID and layer 2 is the specific object instance. So maybe one could also frame it as like the feature model is layer 2 and the morphology model is layer 3, and then behavior model is down here. So the 3 models kind of mapped onto these 3 long-range connections that we have. This is speculative. So
right.
Yeah.
Well, another possibility. Are you ready for another possibility, or you want to finish this slide?
Yeah, go ahead.
A few weeks ago or a month or so ago, I was talking about, I made the argument that, what is an object? If all the features can change and the orientation of the features can change and everything can change, well, what's the commonality between them? And the commonality, I argued, was the location space. That is, an object, not in terms of Monty, but in terms of grid cells, or in terms of the cortex, you anchor all your grid cells in some sense, and that defines a unique space which you can move around in, and that unique space defines anything within that space is the same object. So within that, therefore, everything can change. The location of features, the orientation of features, the actual what the features are, and that would include changes in morphology, because when you move features, it's a new morphology. So in that case, one could argue that the layer 5B cells are voting on the space. It's like saying, in some sense, you could say it's the class of objects. It's like, this is the space that I'm working in. You should be working in this. We should all be agreeing that we're working on the same space, which defines a particular object.
Yeah,
that was an alternate behavior. I'm not saying it's right. I'm just saying that was another way of looking at 5B.
Yeah, I guess the problem that I see with that is that we can apply the same behavior to all these different objects. So if the behavior models how locations can change, then it would be difficult to have.
Right. Well, then I was saying that
location spaces.
Well, that's what a moment ago I was saying. Well, maybe the behavioral model is in the upper layers, because that's where we see those restricted receptive field movement cells in layers 2 and 3. And so, if the behavioral models in the upper layer, it sort of exists independent of the specific space. Right? It's just, okay, here's a behavioral model. I can apply it to cups. I can apply it to bicycles. I can apply it to coffee makers, whatever. And so that would be like, upper layers, I have this behavioral model, and then I project to the lower layers to say, you give me my current behavioral models, how would it impact the current object, which is in the lower layers? All these things.
Couldn't we have the location space in layer 6, and then layer 5B is the general behavior model that can be applied to any location space of any object and just tells it how
right, but when we remember, objects have to vote, and the learning modules have to vote, and we've always talked to now that the learning modules are voting in this layer 2 and layer 3. This would be different. This would be saying they're voting on the object, meaning they're voting on what base object we're talking about. That would be layer 5B. They're saying, okay, we're all agreeing we're talking about coffee cups. We don't know what the state of the coffee cup is yet. And so maybe the upper layers are voting on the particular state of the object, or that would be an alternate alternative. So you'd still have all the same things you have here. It's just relocating them. I'm not saying it's right, or even better than what you're proposing. I just wanted to point out that I was thinking about it slightly differently, and I don't know what's right.
Yeah, I think that's a good point. I think it's actually quite similar to what, maybe if I'm understanding it right, what you're describing, what I was thinking was being voted on here. And one thing I actually am missing in this picture is where they would be voting on the state of the object. So
Right,
yeah,
so,
about that a bit more.
right. So it would be kind of like saying, yeah, we're all looking at us. We agree we're looking at, my hypothesis, I'm looking at, one of my hypotheses, I'm looking at a stapler because of the local feature I'm seeing looks like a local feature in a stapler. But the different, but the different learning models don't know as a whole yet if the stapler, what state the stapler is in. Is it open or closed? Each learning module says, oh, I'm looking at a part of a stapler, but what is its state? So they could vote on the 5B, could be saying, all right, I'm looking at a stapler like something. And then you could be voting on the state of the stapler up above. It's all very speculative. So you're right.
Yeah.
I think one other thing we've talked about that, I mean, yeah, I guess there's lots of different connections, but I think one thing we've talked about before as well that would fit nicely with kind of behavior being modeled in L5 is just the amount of reciprocal connections with L6, because it feels like, obviously it needs to be able to have a huge amount of influence on the location representations that are kind of emerging depending on the behavior
right.
model.
But there's another,
that kind of coupling.
I can make the other argument is that with grid cells, you have grid cells, which are sort of these cells that respond no matter what orientation you're in and how you're moving. They're just location specific in some sense. And then you have to have these motion cells, which lead to grid cells, and they're highly interconnected. So you have to have motion vector cells or velocity control oscillators. So there's this. So one can argue that, I don't know. I'm coming back to counter arguments. I'm going to leave it as still like there are good arguments for both cases here. I'm just I don't feel like I don't think we can make it. I don't think I can make it settle.
One other one, I guess maybe is just like yeah, and kind of I think like you guys were saying before, like they don't necessarily need to be mutually incompatible. Like it could be behavior is kind of more, and modeling behavior is lower down, and then like state as like almost like a single thing is higher up. But that would, I guess, also just make it easier to send the state up the hierarchy. So if you want to influence compositional representations, basically, then that's useful to have in the superficial layers.
Right. The next thing you send up the hierarchy has to be the state of the object. It can't be just stapler.
Yeah. I think what I was thinking, so actually I drew two more connections on here that I had in my like scientific neuroscience evidence diagram. There were like tons of connections, so I just thought these might be relevant if this is the case, is that there's also seems to be a reciprocal connection here, which could work well if we say that the morphological model ID is actually the state of the object. So like what kind of shape does this object have right now? And that has reciprocal connections to layer 5B. And then the other thing is that there's also connections between layer 6B, and I didn't, like the paper didn't talk about if it's 5A or 5B, it just said layer 5, so I'm not sure, but which could have, like, you could learn kind of how, or you could learn how different states influence the locations that should be active in that object's reference frame. So yeah, I put this in gray. Maybe this is info about object state.
One caution, unfortunate, is when the people talk about these reciprocal connections, sometimes people report them, sometimes people don't report them. And one of the reasons that happens is depending on the method they're using. So a connection from one layer to another layer can be onto inhibitory cells, or it could be onto excitatory cells. And so if someone's tracing anatomical tracing of, where's this dendrite project? I made then they'll say, oh, it ends up in layer 5. But if someone's measuring the effect between activating a cell in layer 6 and seeing if the cell in layer 5 is active, they may not see it. And they say, oh, there's no connections there. You just gotta be careful about that.
Yeah, the quotes I have here for that is that layer 6 cells appear to provide a significant excitatory input to layer 5 pyramidal cells.
Well,
So
that
that's
sounds like
on
they're,
one direction.
that sounds, right. Do they say, but then you say they're bidirectional. Do we know that they do the other thing as well? The other direction?
Yeah, dendrites of many layer 6B neurons also reach through layer 6 into layer 5. That's yeah, okay.
That's the
direction.
anatomy.
So I
Yes.
don't,
That's the
the other
anatomy
direction.
one. So that could be onto inhibitory cells. You never know.
Yeah.
And that doesn't throw out those results. It just adds a little bit of like, more things to think about. You know?
Yeah, right. Yeah, and again, all those gray parts are like
That was from layer 6 to layer 5, the first one you were saying, right?
yeah, layer 6.
Yeah, so in the Thompson paper, she writes the majority of intracortical excitatory input to layer 6 comes from the deep layers of like layer 5.
So that's the other direction then. So that
That's
would be
the other direction.
one.
So it is reciprocal, at least according to those two pieces.
Yeah.
I guess just to throw out one more idea, and then we can also just brainstorm more. But one side note on affordances that I thought was maybe if we say there are behaviors voted on in these lateral connections, affordances could be exactly these lateral voting connections. So basically, behaviors in visual models associated with motor behaviors is kind of what I think of what affordances are. So basically, if a vision column has learned, I don't know, like the pinch movement to zoom out on your phone, and we have a visual model of that behavior, that would be voting with the behavior model in like the motor cortex of your fingers pinching. And since, yeah, basically if I'm seeing that behavior, the vote would kind of invoke it here, or if I'm invoking the behavior here, I would kind of expect to see this behavioral change on the phone. So that's kind of what I was thinking. Maybe that's how affordances are implemented.
Let me try to absorb what you just said.
Would then, just to check, I understand, because is this for like the vision model to almost enact that behavior in the touch model? Like because that feels more like the kind of goal state that you project with like L6.
It wouldn't be the goal state. It would be more like, so the vision model wouldn't have learned. I mean, pinching, maybe that's a bit of an abstract example on the phone, but the vision model doesn't know about how the hand works and how the hand grasps a cup or something, but it knows how this behavior looks like. So it knows how the hand looks like when it grasps, and it can recognize that behavior.
Let me give you an alternate thing that's sort of counterfactual of this. Imagine the behavior is a door lever, like a doorknob. Instead of a knob, it's a lever, like a bar, and you rotate it down, right? So the affordance is, oh, I see, right now I'm looking at the door in the conference room here, and it's got one of those levers on it. I can do that with anything. I can do it with my knee, my shoulder, my elbow. There's lots of ways I can move that down.
But
so
I'm not sure if that would be an affordance. Like, it's not like you look at it and you just think of moving it with your knee.
Well, no, but my point is, I know that it has to move, and it's independent of what I move it with. So to me, it's not associated with a particular, it's a movement of the handle itself, as opposed to how I'm going to move it. So I'm just saying
sure.
It's like on the screen, on display, you have to use your skin, otherwise it doesn't work. So I picked something where it's completely independent of what physical thing I use to move it.
Yeah, so I think like how I would think of it is the doorknob and its behavior of twisting, that would be modeled like in your vision column. You model how the doorknob can transition through the states of being twisted and turned, and how that changes the state of the door even. But then naturally, when you see a doorknob, you kind of have this affordance to grab it and open it with your hand. So that would just be kind of through the voting bias towards that. But it doesn't mean that's the only way you can do it. You still have that model that the doorknob can twist, and that's independent of how you actually twist
Right,
it. It's just
right. Well, then
it's
I
like,
could probably come up with examples where there isn't a preferred way of doing something. I
and
mean,
then you don't have an affordance. I think that's just the different, at least how
oh,
I understand
interesting.
the
Oh,
definition
okay.
of
So maybe I'm
affordances.
using the word affordance wrong. I thought affordance was to me, the word affordance, as I've used it in my past, is something, something physical about an object that suggests how it behaves, and how it could be manipulated. It doesn't suggest how I might actually manipulate it. It just says, it's like the stapler. The stapler, I see a pin and two bars. I say, oh, that's a hinge. Maybe that's a hinge. And that feels independent of any way I might actually move the stapler. It just doesn't, it feels like the affordance is just part of the property of the object itself as opposed to how I'm going to actually do it. So maybe that's different than the way you're using affordances.
Yeah, I guess that would be just, yeah, in that case, that would just be in the model of the behavior itself that you're
That's-
observing, like how it can move based on some features that you detect in there. Like, yeah.
Well, I guess that's how I was defining the affordances. You may be defining it differently. It sounds like you're
Yeah, I
defining
think
it.
I was thinking of it a bit differently, like,
Is
but
there a
maybe I'm
technical,
thinking of it wrong.
I don't know, maybe is there a technical definition of affordance that, if I looked up in the dictionary, what would it say? It's like, I don't want to use it in a way that other people are not using it.
Yeah, I'm just having a quick look. Affordance is what the environment offers the individual.
Well, that's okay. That's pretty
Yeah,
generic.
yeah, but I think, yeah, I would say, yeah, I'm also kind of thinking of it like you're saying, Jeff, that it's like it's kind of a property of the object that's fairly independent of the specifics of how you interact with it.
And
So like an affordance is like being able to hold fluid or something like that.
Yes, so in that case, it would be more like the features on that model kind of inform what behavior that model has, like which behavior you would detect here would be
right,
informed by
right.
features on
So
there.
some
Yeah, then
learning module sees this feature of the hinge looking thing, the pin, and it says,
yeah,
oh, this could be a moving hinge point.
yeah, I guess
The other,
yeah, this is more than an example of how sensorimotor how do you call it?
how we might
Coordination,
act. Yeah,
sensorimotor
well,
coordination
because,
work well.
but I was reacting to your first line, which says affordances are
Yeah.
encoded as lateral
Yeah,
connections.
so then I was using this term too narrowly. Yeah, if
Maybe.
that's, yeah, then affordances can be just encoded within one column of
It
feature
could be
spikes
encoded
in the
within
model.
the feature, within the states of an object, observed state changes of, objects.
Yeah,
The nice thing about this is we're getting closer to having all the right terms and the right words and the right components of the problem. I don't think we're there yet. We're still disagreeing about some things, or we still don't know about some things. But we're getting closer to it.
yeah, I think,
yeah.
yeah, that was another reason why I wanted to just put this all together, because we had like a long Slack thread about it, and there, like lots of terms were coming up, and I just thought like feature, morphology, behavior, states, those are like key terms that kind of, yeah, it's just kind of good to go over again.
I'm gonna push again to think about the argument I made earlier, which is that, objects are defined by their space, and then an object in theory could have any set of features poses within that space. And then using that as like a generic idea, like, okay, these are all the different things that this object can exist in, and then how do we transition between them? It's just a little bit more generic way of phrasing it. I'm trying to get rid of that morphology thing again.
Yeah.
I thought that was a good progress to get rid of morphology, but maybe not.
Yeah. I just wrote down a few kind of open questions. So this one we already talked about. Do behaviors need to be path integratable? And then the second one I was briefly thinking through, but I think not. So could rotation just be a specific type of state? Could we use the same mechanism?
The
for
rotation
states?
of the entire object?
Yeah, like object rotation.
I don't think so.
Yeah, that's yeah. The
You know,
conclusion
what it could be, you know, if I have a compositional object, in some sense, all things are compositional objects, then the orientation of a feature is part of the state of the parent object.
Yeah,
But the child object on its own, I think the model would be independent of its current presentation to you.
yeah.
I would think.
Yeah, I was just thinking through, like, I guess this one is a bit more of like an engineering question as well. So like with rotations, we kind of test through different possible rotations, and depending on which rotation hypothesis we have, we expect the features and locations to be in different locations relative to the body. So kind of a similar thing applies to state. If the object is in a different state, you expect features and location to be in different places, to be different, but you kind of have to test different states of like state hypotheses basically of the object. So yeah, that goes a bit into like how would we implement recognizing the same object in different states.
Well, that goes back to the point we were making earlier. Like it seems like we have to be voting on that somehow. Right. It's insufficient to say these are all staplers. We have to say, no, this is a stapler in this position. In a flash inference vision, I would see the state of the object. So somehow we have to reach that by voting.
Well, I mean, even a single learning module can like be rotation invariant. And the way we do that now is by testing multiple hypotheses. So
right.
I think what you're saying, Viviane, is that we have to test multiple states. And so does that mean there's some kind of almost like symmetry or whatever between rotation and state?
But the way I think about this, remember that we're relying on the thalamus to overcome this rotation problem. You know, it's like, okay, I don't want to have different models of the object, and every orientation of this coffee cup to my body shouldn't be a different state of the object. I mean, that's just I don't want to encode that. I just have this model, and then it's a temporary problem of how do I, you know, convert my senses and my movement behaviors to the current orientation. So to me, that was like a real-time compensation being accomplished by the thalamus, whereas the state of the object is really a property of the object.
I would say it's more a property of the behavior, because like with the running banana, we don't have a model of the banana in every possible running position. We have a model of like how this behavior changes the locations on any object.
Well, but be careful when we talk about the running banana. Now we're mixing a behavior learned in one place with an object learned in another, which is fine, which is great. It's not an inherent property of bananas that they run. We'd have to see people running. We learn the model that way, and then we try to. So it's a great example, because it just reminds us that we have to be able to learn models of behaviors that can be applied independently to an object.
Yeah.
Like when I see the banana running, I don't think, oh, there's a person running. Oh no, it's a banana. It's like, oh no, it's something's running and it's a banana. I can even imagine a non-describable object that's running, you know.
Yeah.
You could just look at the, you know, if you had a bunch of those, I forget what they're called when they put the little white dots on you, the ping pong balls, and they do the motion capture. You know, you can just see a bunch of white dots moving and say, oh, that thing is running. You know, it's like there's no object there. It's just running. You might imagine an object there, but yeah.
I guess.
All right. So I guess I think I'm agreeing with your I think maybe not, and I don't think so. Well, I think the first one might be maybe yes. The second one I would agree with you. I don't think so.
Yeah.
Yeah, and then I guess that relates to the big question that I haven't really answered here, is like what mechanism could the brain use to model general object behaviors that can be applied to many objects?
Well, that was my point of,
yeah,
if you had a state, if you had a space of states, like I argued a month or so ago, then then that could be applied to any object because it's independent of the object. It's just it's how various pieces of the object are moving relative to the other, and it's independent of the actual object. So
yeah, it's
I
guess I'm still a bit unclear on if every object has its own location space, how do you have a model that tells you how locations of features change and then apply it to different location spaces?
right. Well, it's I don't know yet, but it seems like it's quite doable.
Yeah, it must be.
Yeah, it must be doable. So it's like there was an answer to that question. Just because we don't know the answer doesn't mean we give up on it. It's like okay, it seems to be happening somehow. I don't know.
Yeah.
Interesting.
Yeah, that was everything I had. I don't know if you want to do more whiteboard brainstorming or if you want to just kind of sleep on it for a bit and yeah, go into the mini columns idea.
Well, one thing I just wanted to comment on with the presentation, I just thought it'd be interesting to touch on again the L5 voting thing you were talking about with what initially you were calling affordances, but yeah, as you were saying, it's more about like coordination. Just because I think it is kind of interesting that like we might send goal states, but then also have some bias to a particular what do you call it, way of solving it. And I think that's kind of what you're like showing there, is that like it wouldn't enforce a way of doing something because it's a lateral connection, and so it's not going to on its own instantiate a particular representation, but it could be like, oh yeah, generally when I'm doing this with my, or like when this behavior is happening with my eyes, this behavior is happening with my hands. So yeah, that's interesting.
Yeah, so I'll throw in more complications here, and I might have alluded to this recently, I can't remember. When I think about what's actually going on in the brain, although it's possible for a single region to learn behaviors and learn objects, what typically seems to be happening when we learn a new object, we learn it at multiple levels, actually higher up in the hierarchy. Like I don't want to dedicate V1 or S1 to some new thing. And so we build a model higher up in the hierarchy, maybe even in the hippocampal complex. And it's temporary. Here's a new object, I'm looking at it. And now when I want to actually interact with the object, I have to basically say, I have to move back down the hierarchy and pick a specific way of interacting. And then it's as we talked about with typing and playing the piano, things that you do over and over and over again can be learned very low down in the hierarchy. So I don't have to go up and down this hierarchy. I can just type without even thinking about it. But in the beginning, I have to think about it. In the beginning, I have to choose what fingers to use. And so it involves multiple hierarchical levels. I only mention this because this is another complication when we think about, how am I going to type or how am I going to move the lever? In the beginning, I may not have a preferred way. I just say this lever has to move or this button has to be pressed. And then it goes down the hierarchy and it says, well, it's easy for me to use my finger, or it's easier to use my hand, or it's, whatever, it's as opposed to some sort of learned thing. Only with this really high practice do you actually assign a particular, I see, I want to type a word and I go right to S1 and M1 or whatever and then type it. It's just more complications in this process. So in some sense, separating out what I typically might do for how I manipulate a new object with it and how I might manipulate a highly learned object would involve different levels of hierarchical composition. So it just makes things much more complicated to think about for me.
I guess another reason why I was thinking about these lateral voting connections, like voting on behaviors, is because when we talk about the goal policies, it's always it seems a bit difficult, at least when I'm thinking of it, to have the same model that recognizes the behavior also output the actions to transition to a new state. And it just seemed like
why is that hard to imagine?
Well, just because like the vision column that actually sees I don't know, the key going down or the light switching on doesn't project subcortically to whatever controls the finger, it moves the eye. So it would be nice to have kind of this behavior model of the lamp switching on in the vision column to recognize what's happening, what behavior is happening, but then it being associated with behavior model in more the motor
Well, again,
cortex.
this gets back to the point I was just making, is I think there's hierarchy involved in many of these behaviors unless they're practiced and rote. So, you know, S1 or V1 wouldn't be informing S1 directly on, even take a lamp. I walk into a room with, you know, unless this is like a lamp on my bedside, I touch it every night. I know exactly how to do it. I don't have to think about it. You know, I see a lamp, I have to find the switch. I have to then reach for it. This involves a fair amount of the cortical hierarchy, I believe, because it just has to, and it seems like it does. You have to think about it a little bit. It's not like it's mindless. It's not mindless. You have to think about it. So where is that? Which time am I going to reach it? Yeah. So again, I think some of those thoughts you just said, Vivian, get complicated or get different answers when you're assuming or not assuming it's a highly repetitive one procedure, or if it's going to involve hierarchy.
Yeah.
Yeah. Anything that goes within a primary region and between primary regions, to me, would be super highly learned objects or behaviors. And so the most examples of like the lamp wouldn't fall into that category. Even the stapler probably wouldn't fall into that category. Different staplers, you pick them up different ways.
Yeah, I guess what I mean is like you can have a very learned model of the lamp turning on or the stapler, just kind of how it looks. But then you can invoke different behavioral models of how you might apply pressure.
So then I would argue then that that's going to always involve a hierarchy. It's not, it can't be done primary region to primary region, because I have to have some point where I say this thing has to move or this has to press, and I have choices on how to do it. So if there's choices, it has to go down a hierarchy to go different routes. I can't have the vision V1 connecting to all different fingers that might push the button. It's more like, oh, a button has to be pushed. I'm in a novel situation, so it starts higher up and says, okay, what do I have to push the button? I can use any of these different physical parts of my body to do it, and just pick one and go down the hierarchy.
Yeah.
Or pick another.
Yeah, that might be, that might be more of a temporary environment model of like where your body parts are right now.
Right. That's why I mentioned something that's extremely highly learned, like maybe a lamp on your nightstand. You could just reach and do it and not think about it at all, because you always grab it in the same place, you always push it with the same finger, and it always behaves the same way, and you've done this 1,000 times. Then you might be able to do it like that. Or just like, also, as I talked about, like playing piano. You know, a pianist can recognize phrases or sequences of notes quite long and recognize them as one thing, and their fingers just do it and they don't have to think about it. Or an athlete, you know, same thing. But for most people, we have to think about it, decide, oh, which finger to move and how to get it there.
One thing I was just thinking with the time we have left, I feel like Vivian, Jeff, and I have had a lot of chances to talk, but yeah, hopefully we've not been sucking all the air out of the room. So yeah, I don't know if anyone else had any things they wanted to add.
I think that would be
well, it's just a lot to take in. There's a lot of detail here on particulars of the model, so I'm still just kind of processing it, absorbing it.
That means it's hard.
Yeah.
Is there anything that's unclear or that would be useful to get some more details on?
Well, I think the part that I'm like, I don't know that there's any more details at this point. I think I've been thinking about behaviors as being pretty closely linked to the underlying object model, and the idea of sort of abstracting away the behavior away from the morphology of the model to make it more general purpose. It's a fairly difficult kind of thing to picture exactly how that would happen.
Agreed.
Yeah.
It's hard to picture.
Yeah.
To think about.
Yeah,
We
one
have to think
thing,
about it. We have to think about it.
I guess next Wednesday, maybe Hoje, you'll probably be talking a bit about neurops and stuff. And then I think the 2 Wednesdays after that, there's holidays. Although maybe the week of January 1st, we could do a research meeting on another day. But
Yeah.
but I was thinking maybe one thing could be useful. So like a while ago, we talked in terms of like concrete ways of doing behaviors and stuff like that. We talked about sort of like essentially what's like message passing in graphs, where like nodes are kind of sending messages to one another versus like learning sequences. And I could try and kind of give a summary of some of that discussion that we had and stuff like that. And that might help us kind of just rethink about, or like think again about possible like concrete proposals.
Yeah, I thought that was an interesting part of that was interesting because I think we talked about learning like general purpose edges and nodes that can be reused in many different objects. Like you might learn how a hinge works, and then you can apply that hinge behavior to edges in all kinds of graphs. So yeah, I think that was an interesting idea.
Go ahead.
Oh no, yeah, nothing really that.
So, it's funny because at one point, Viviane had said, "Oh, when we get together in February, I keep again. What are we calling it? It's not pilot. It's
VP retreat.
Retreat. Yes, seems like an easy word to remember. Maybe we can make some progress on this whole object behavior stuff and object state. So, in my mind, what we're doing right now is sort of prepping ourselves by thinking about these problems over and over and over again, which historically, this is what it takes. You have to just pound your head against the wall over and over and over again on the same topics. And then after you do that enough time, then the answers pop out. So I view this as all preparatory to like maybe sometime in February figuring this all out. So that's my goal.
That would be great. Yeah.
I know, but to do that, we have to sit here and get puzzled over and over and over again. I've always found that somehow that works. You just rethink the problem. Oh yeah, we forgot about that idea. Oh yeah, there's so many things, and then somehow at the end it settles down. So I think these meetings are very we're making good progress, even it may not seem like that. It's what we need to do to move towards a solution. So that's my goal. February, beginning of February. Maybe that would be a nice thing to do. Figure this out by then.
Yeah, I guess related to that, at some point, I mean, I keep saying I'm going to give an overview of the connectivity in cortical columns. I could also just share my big paper at some point, because today when I was making these slides, it kind of felt a bit like a puzzle, where I would go into that sheet and look into all the evidence and all the different connections and try to kind of piece the pieces together and figure out which parts could be doing what properties do the neurons have in the different layers and stuff. So yeah, I think just kind of having that context again in one place too could be useful.
Totally, I agree. On the other hand, I would argue that looking at that graph will never tell you the answer. It's like all progress, you have to have this sort of empirical evidence and theory, and they have to inform each other because there's so many unknowns about the anatomy and physiology of the cells, and so many details that are relevant that we don't know which ones are relevant. That just I have found looking at it alone is not sufficient. But when we come back in, like we're doing today, with sort of theoretical constraints and say, well, it has to do this and it has to do that, then you can look at those diagrams and say, oh, yeah, I remember there was a connection for that. Well, yeah, that makes sense. And this explains that physiology. So,
yeah, it's funny because in some ways it's like a highly unconstrained space. Like so many things are connected to so many other things that you could come up with all kinds of crazy theories or whatever. But it's nice how you kind of start with like, okay, feature inputs are coming here. Like movement information is coming here, like that kind of grounds it, and then like as you say, kind of like slowly building it up.
Right. It's this iterative process between theory and empirical data, which is the hallmark of all scientific progress. And we have to do both. We don't do the empirical research, but we have to read it, interpret it. And this is why, over the years, many neuroscientists have said to me, oh, it's impossible to figure this out. You can't figure how this works. It's just too complicated because most of them don't think about the theoretical constraints. At least a lot the way we do. Think about it very narrowly. So that's our unique value add here. If we have a second or two, I'll just, if you
Cool.
don't mind, I'll just give you a teaser of what I wanted to talk about with mini columns.
Can I make one comment about what I thought about the whole
Sure.
behavior model, and then it's yeah. So I guess what's been on my mind was how we can generalize behaviors to different kinds of, like, let's say pouring behavior to all different kinds of cups, or sitting behavior to all different kinds of chairs or flat surfaces. What I think babies might be doing, and babies try out a lot of different things, and like somehow implicitly they're sort of learning the physics of how things would be, right? That way they can predict what will happen even though something is new. Like for like a AI system, maybe behavior is something that we can. I don't know if we can like encode behavior, like, or like what can be done or affordance directly, but we can keep like a observation action pair. So like it did some kind of action. Here's the like resulting observation. And the difficulty is to be able to kind of generalize that. So if I was able to pour water into this cup, then we wanted to know that it can also pour water into this cup. Sorry, dirty water and coffee. So but then I think that observation and action, like somehow we're not just connecting that between this cup and like this particular cup and that particular action, but somehow from this cup we're extracting, oh, like this is within this cup there's a concavable feature or a wall feature that makes it pourable. So like we need to associate that observation and feature not to its specific ones, but to its kind of general feature level. And I don't know how to do that, but that's how I'm thinking of actions as like a sort of a
Well, it seems similarly like with,
emergence.
I think that's right. And Scott mentioned something very similar. It was like, how do you separate out behaviors from objects themselves, right? We want to have the behavior somehow exist independent of the object. Of course, when you're thinking about pouring to different cups, I'm thinking like, oh, I could put fluid into a shoe, which is much more unusual.
Yeah.
Yeah.
But both have
So,
a concavable surface.
well,
So
yeah, I
that
guess.
feature must be
Yeah.
shared
Right.
across
And
cups and shoes.
You're right. And then you think of like a shoe, well, but if it was an open toe shoe, I know it wouldn't work.
Yeah, exactly. It's almost like a mental simulation where you
Right,
play
right.
out what effect would happen,
Right,
at least if it
right.
was a novel object. And
And
then,
then-
yeah, eventually you could learn like just by rote almost like, okay, a couple like things you can pour into, but you kind of almost need to mentally simulate the fluid going into it and how it will
Right,
disperse.
right.
And
Right. It's more than just like, oh, it's a container. It's like, oh, it's a container that's waterproof or has no holes, or, I want one that has a rubber shoe would be better than one that's, fine leather. It's like all these things play out in your head as you're about to pour the water into the
or like
shoe.
a paper bag that's going to like collapse. Like you can kind of pour liquid into it, but
So I think, Jose, this is the key of one of the things we're talking about here today is just how do you separate out behaviors from the objects in which you observe them. And I think just stating that problem is a long way towards solving the problem. Just knowing that you have to be able to do that. It just gives you, and assuming that somehow happens on a column by column basis, it tells you a lot.
well,
it puts a bunch of constraints on the problem.
one kind of maybe interesting experimental thing that just came to mind was that in terms of like, we've talked about, wow, okay, each learning module is learning physics kind of to some degree. That seems like fairly complicated, but I just remember once doing rotation with this guy called Kevin Smith, but he was in Joshua Tenenbaum's lab. And Joshua Tenenbaum's lab do a lot of stuff about like intuitive physics in humans, like how humans have this kind of notion. But what was interesting, I just remember asking him, like, is there like a region in the brain that like you lesion and that people don't have physics kind of? And I remember him saying that there wasn't a known one. Like, a lot of times people talk about like a face area or whatever, like all these different things, but it really did seem like physics is a very distributed thing, which I think fits well with the idea that kind of any model that might be subject to physics is going to be kind of where it's learned. So I thought that's just like, that's nice support for kind of the general approach we're taking, where it's not like, oh, we have like a totally separate part of like these learning modules are learning physics, and these other learning modules are learning
Right.
objects.
Right. So
Yeah.
physics
I
is
agree.
it's sort of an emergent property for most people of observation. In fact, to really understand physics, you got to go to, take university classes for quite a while to really understand what the physics is. Other than, you kind of know, like, oh, this works this way, but then you say, well, it takes a Newton to figure out why did it work that way.
Yeah, it's almost like language, like your native language, you use the grammar perfectly, but if someone's like, oh, this is past participle, whatever, like,
You say,
what the hell does that mean? Like, yeah.
Exactly. It's right. I mean, the rules are not, we don't encode rules, we just go encode observation.
It
good.
sounds like, based on the hinge comment, like composition might be a good way to sort of get us out of this abstraction problem, like how, a behavior could be applied to many different objects. Like you identify that there's a hinge, and so through composition and identifying the objects that enable the behaviors, we can sort of abstract it to many other kinds of compound objects.
It does seem almost a requirement to see an affordance or see a possible behavior. There has to be some physical attribute about the object you're observing that suggests that behavior. If I see a sphere, I'm not going to assume there's a hinge there and I can open it. Maybe if I saw a seam around the sphere, and maybe a little thing that looked like a hinge on the side. So my point is that there are associations between the behaviors and the physicalness of an object but it can be done locally, as we said earlier. You can observe in a local feature that invokes a behavior model, and but there has to be this connection somehow. There's something about physicalness. Jose was talking about the shoe. Like, oh, there's vertical edges, or there's an opening or something. There has to be some physical thing that connects the two, even if it's only a subset of the object, that suggests there's a behavioral aspect of it.
But
Sorry.
I was just going to say, I think, but what you're saying, Scott, is true that it will simplify a lot. Like we'll need a lot less specific behavioral models that we learn if we can compose behaviors into each other. Like the running person is a bunch of limbs that move in certain ways, instead of having to model each part individually. And I guess that reminds me a bit of another point that, like you said, Jeff, like sometimes you talk about something and then you forget it again and then you remember it again. So I just thought of it again, but way back another by the bay when we were brainstorming, we talked about how we can't really recognize behaviors in one column at a time, like that we actually need some flash inference to recognize the state of the person, because if we have a running person and we only have one sensor, by the time we move the sensor, that part of the person is in a different place again already. So that, like, especially for modeling states and behavior, especially for modeling behavior, states not necessarily, you need to do need a lot of voting to kind of see the change in states.
Yeah, I guess if I was looking through a straw, it might be hard for me to learn running. Right? All I could see is one little piece at once. It might be hard to learn what running.
Yeah, I'm glad you brought up that example again, Vivian. I'd also forgotten about that. That we kind of agreed that I think it was the Elvis Presley dance. Oh no, what was it? Yeah, we had like a John Travolta dance. Like we had a few different examples, but we were like, yeah, you can't learn this really with the straw world. Do
you? I mean, maybe very simple ones, like if you have a tiny button and if you press, it changes color. Maybe you can learn that behavior, but more complex and compositional.
Or if it's
ones,
like really repeated, like I don't know, if a state was opening and closing again, you just keep going over it with the straw, like you'll eventually kind of be able to kind of mentally map.
Right,
but it's a lot harder.
We take a lot of observations. Yeah, interesting. I forgot about that. I still forgot about it, but it sounds like something we would have talked about. Niels, you remember the specific dances. That's pretty good. Oh gosh.
but sorry, I think Scott, you were going to say something too.
Well, I was thinking about the composition of behaviors and all that, and thinking that there might be multiple solutions for different kinds of problems. Like the hinge solution might not be the same as knowing that something holds water. Those or continuous deformable objects, like it's less clear how to turn that into a composition or something like.
So I was making that argument about thinking very, very conceptually about behaviors. Is this any change in a model as long as we're in the same location space? And so I'm trying to get around that issue, Scott, where you say, oh, it's hard to imagine this as being the same as that. Containing water seems very different than a hinge.
Hmm.
And I think the answer has to be, science, it doesn't have to be, but the answer is likely to be that the column doesn't make it, the column really doesn't know these distinctions. It just observes a few basic things and says, well, all these things are part of the same object because I'm in the same space. I haven't moved on to a different space. And somehow we can learn any of these things. That would be the nicest solution, right? The nicest solution would say, yeah, we can come up with 100 different things that might, variations of this theme, but they all fit into this idea that there's a space for the object, and then different states represent the different compositions of the object at that moment in time. And somehow that encompasses all the things we just talked about. Because we try to solve,
Go ahead.
No.
Sorry. I think in the pouring water example, it seems actually more like it's a behavioral model of the liquid than a behavioral of the cup itself. And then kind of like the point that Niels made, that we're actually just simulating the behavior of the water and applying it to the cup instead of the cup having the model of being pourable or something like that.
I don't know. Doesn't it seem like if I see a bunch of cups in a cabinet, I know they're all suitable for putting, tea in them.
I feel like you eventually learn that, but
I think you can only learn it if you've observed it in some object. So pourable water has to be observed in something before you can
I feel
say it
like
exists.
you can't just simulate the water. It's like the interaction between the water and the physical object.
So initially you see the behavior attached to a particular object. That's how you learn it. Maybe then you see it another object and somehow it invokes the same behavior, even though it's a different object, and you say, oh, I can apply this to this object. And then eventually you can say any object that has a set of properties, it might be pourable into it. All right, we're repeating ourselves. We already lost Jose.
One quick thing I just wanted to say, Scott, related to what you were saying. So I'm not sure if this is right or whatever, but one thing I've been thinking kind of that I think relates to this is how maybe some behaviors it's almost a little like model free versus model based, where you can imagine some behaviors are learned kind of like as an arbitrary sequence, and that sequence can be anything, but you just kind of learn it almost by rote. And then some behaviors are more like a more kind of general computation where you're thinking about how it evolves or something like that. So I don't know. In some ways it'd be nice if it's just a smooth continuum, but maybe it's also more like an actual separation in if you've seen a totally new object, then you just learn this kind of very idiosyncratic behavior, but then there's certain things that you're able to kind of disentangle and then generalize across different things.
Right. I have a lot of ideas on this, but we're out of time here. I didn't get to say my mini column idea. Should I leave it for next time?
It's up to you. I mean, I'm free for a few.
Okay.
I don't know if everyone else is.
Yeah, I'd be curious.
Yeah, just to make it started with an interesting observation. When we move our limbs different ways, we have to use different muscles, right? To extend my forearm is a set of muscles, and to retract my forearm is a completely different set of muscles. It's not like I can just send a command to the muscles like move this direction, move that direction. I actually have to send muscles set A contract or muscle set B contract. And then it occurred to me that mini columns, one of the things that always puzzled me about mini columns, well, well, is that, it seems like they represent movements in a single direction. And a different mini column movements in a different direction. But when we kind of come up with like grid cells, we want grid cells to be independent of the actual movement that led to them. So there's this tension, this dichotomy between we want representations that are independent of direction of movement and ones that are sometimes not independent of direction of movement. Well, so the thought that occurred to me, and this is very simply stated, if we think about a mini column, and someday I'll have to review exactly what the mini column is, but it's very, very skinny, right? This is 120 cells vertical. What does layer 5 cell in a mini column represent? Well, it could represent initially in evolution, it could represent a contraction of a specific muscle. It could have said, to affect this movement, you have to contract this muscle. And another mini column says, if I want to move the other direction, I have to contract a different muscle. Now, that's not the way it works today, but that could have started that way in evolution. And that could be defining a language to help define a language of layer 5 cells. When they invoke a movement vector, I used to think like, oh, they encode some sort of movement like move, in some compass direction, but maybe they're not. Maybe they're just individually saying like, more like, contract the muscle or move in this direction, or if I want to move another direction, I can invoke another mini column and then another one. That's the idea. It's very simple, but it was an interesting idea that evolutionary might start that way. And maybe when we think about the motor output of the cortex, we should be thinking about these encoding movement output in the cortex in this manner, sort of individual cells representing movements in individual directions, which makes a lot of sense, I think.
So this would be movement relative to the body, like in.
It just doesn't really matter at this point. It's just in a column, whatever the column is representing.
It's not relative to the object reference.
Well, it could be.
frame.
Well, it would be if it was an object. If it was a learning module that's representing an object, it would be relative to the object reference frame, and then that gets converted to the body's reference frame. But it would be initially generated relative to the object. But remember, I've argued that layer 5 cells might be doing the same orientation transpose that the thalamus is doing, and so when it starts out in the cortex, it says I need to move this relative to the object, and then it gets converted right before the layer 5 cells themselves convert it to like move it towards this thing relative to the sensor or to the thing I'm moving. I think it's just a saying when I think about layer 5s representing movement vectors being transferred someplace cortically, maybe the right way of thinking about them, individual cells represent movements in different diametrically, opposed directions. And so imagine if I was moving my finger in a circle, it would clearly involve a whole series of mini columns invoking in sequence, as is each muscle has to be invoked in different points in the circle. It's a very simple idea.
That's interesting. Do you know if there's, because I guess with like the mini column, if they stick a probe in perpendicular to the surface of the cortex, they can see like a very distinct response profile for the sensory ones. Do you know if there's anything like similar where they've tested?
I don't know about it. No.
Yeah, because I'm just wondering, because I can imagine if that was present, then if you stimulated throughout the mini column of L5, you would basically get the exact same. But then as soon as you move over, you'd get a different contraction.
But then, so imagine now that if those movement cells all representing, it's an observed movement of the sensor, right? So you're observing a movement in some direction. Then the layer 5 cells initially would fire the same way, basically saying, okay, I'm part of that. I'm going to fire when we're observing a movement in this direction. And then that layer 5 cell would then associatively link to the muscle that was actually making it move in that direction. And so the layer 5 cells learns to like control a muscle that actually led to the movement that was observed in one direction. And then later we can, without the input, you can say, oh, we want to move in that direction. I now know what muscle to contract. What cell fires. I forgot your questions.
Oh, it was just about the experimental evidence. Like,
so
obviously there's a lot of things that are hard to decode, but it seems like this might be actually tractable.
Right, but I think what happens is when they measure these cells, almost all these experiments were done using like sinusoidal gratings. So the animal's not really thinking. The animal's not really observing a real object. It's just, you will see the layer 5 cells fired the same way as the layer 3 cells or the layer 6 cells. They're all like tuned to the same
But I
thing.
guess because if it's a motor output, it'd be interesting if they actually stimulated layer 5, what happened?
Right.
If they stimulated a particular mini column,
Right.
and like whether you see that kind of same almost like invariance within the mini column, and then but changing across the mini column.
What would be really cool is also to say if the animal's awake and observing something it knows, you would see the layer 5 cell fire before the observed change in the other cells. So the layer 5 would precede, it would basically generate the movement that then gets observed. That would be a great experiment too. I'm not aware of anyone doing any of these things because they don't really have theories about why you should do those experiments. So they generally wouldn't pick up on them. But maybe someone has. I don't know. I'm not aware of it. Anyway, that was the idea. I'm working on mini columns is trying to really get to the core. It's another piece of the diagram that you didn't have there, Viviane, in your diagram. It's another piece of the puzzle. The thing about mini columns is these independent units and how to interpret them as part of a greater whole. And if you go read Mountcastle's work, he actually argued that the mini column was the unit of replication in the cortex. He didn't argue that the cortical column was. He said mini columns are the computational unit, and you take a bunch of mini columns, and now you have a cortical column, and it does something. He had no speculation at all what mini columns did, as far as I know. But he said they're observable, they're physical, they're there. They have these common properties. The cells in a mini column have certain common properties. Therefore, he said this is the unit of replication. And take a bunch of them together, and you've got a cortical column, and it does something bigger. So I'm working on that right now. I think I have some interesting ideas about it. But, so hopefully before February, I'll get to present those ideas. Or maybe I'll just write them up at some point. Anyway, that was just that's it. It's just it's like, oh, what an interesting idea that these layer 5 cells could have started by just actually activating individual muscles at some point in the past.